Okay, we're at section 1.3 now, where we're going to talk about scientific measurement. Now, this section has a lot in it. So even though the section is only really, I guess, about 4 pages, 4 or 5 pages, there's a lot in here. The author has packed in some very deep issues in terms of what we do in chemistry. We can talk about all sorts of things about matter. We could talk about properties of matter and such. But at the heart of the sciences is what we call measurement. There's a big difference between how we think about the universe in the sciences compared to really any other field, whether it be English, literature, or history, or sociology. At the heart of the sciences, the natural sciences, the physical sciences, is the issue that measurement is paramount, meaning it does not matter how beautiful your idea is. Measurements will determine the validity of your ideas. So, although Albert Einstein's theory of general relativity is a remarkable achievement in our understanding of the universe, if it cannot accurately describe a measurement, a proper measurement, then it's nothing more than just some idea. Okay? So, what we're going to talk about in this section is the idea, really the basics of what a measurement is, and then look at a few examples of those measurements. Okay? So at the top here is a figure out of your textbook of some common laboratory glassware. And the one on the left is what's called a volumetric flask. Then one just to the right of it is called a graduated cylinder, followed by a volumetric pipette, followed by a burette. And these are all devices that are used to make measurements of liquids. Could be water, could be a dilute solution of acid or base, could be a saline solution, but some kind of liquid solution. Okay? And these ones, all four of these are designed in such a way as to allow you to measure how much of the liquid or the solution that you're measuring. So, for example, when we cook, we might be familiar with measuring out a cup of water or a quarter cup of water. The more typical units that we use in chemistry are not based on the English, the imperial system of cups or teaspoons or tablespoons. They're based on what's called the SI system, the System International. It's a set of units that are commonly used. So below that in table 1.2 are what are called the 7 base units. These are what we would consider the most fundamental measurements that we can make in nature. And it's somewhat interesting when you think about it. So the first one you're familiar with is length. We all know how to measure length. The SI, base unit for length, is the meter. And all other lengths, all other units of length are derived from the meter. So for example, if I say, how many centimeters is that? The base unit that we use is the meter. The centimeter is converted from the meter. The inch is converted from the meter. There's mass, right? So the universe has space, so it has extension, it has length. The universe also has mass. An atom has mass, an electron has mass, a person has mass. The standard unit of mass is the kilogram, and the abbreviation for that is kg. We'll get to prefixes. Kilo is what's called a prefix. We'll talk about that in a moment. The universe also has time. There's time. We measure time. And the unit of the SI base unit of time is the second. The symbol for second is S. You should memorize these symbols. So you should memorize that M stands for meter, kg stands for mass, S stands for second. Now we're not going to use in this course, in fact you don't really get into this until you take the second semester of chemistry or the second semester of physics. There's also electric current. That's also a standard base measurement. And the unit of electric current is the ampere, and the abbreviation for that is an uppercase A. We're not going to use that in this course or the next. A temperature, the standard SI unit, is the Kelvin. Okay, it's temperature, and normally with temperature we're used to degrees, but the Kelvin doesn't have degrees, it's just Kelvin, and the capital K refers to that unit. Amount of a substance, we'll use this quite a bit later in the course, is called the mole, M-O-L-E. It's a measure of how much of something you have. Okay. The symbol for mole is MOL. And then luminous intensity, to be honest with you, we're not going to use that in this course. You're not going to use this in general chemistry. It's even relatively rare to use that in a physics course, but just for completeness, it's here, is the candela, and the abbreviation for the candela is CD. Okay. So those are the base units, meaning anything that we measure should be either one of these measurements, one of these 7, or it should be derived from one of those 7. So let me show you what I mean by that. If I were to say that I'm going to measure the area of a square, well, we know the square, the area of a square, is just the length squared, right? So the area is length squared. Well, let's use our standard SI units. For length, it's the meter. So the units would be meters squared. So notice what we're doing here. When we make a measurement, we might need to do some sort of mathematical operation. We do that mathematical operation not only on the numbers, but also on the units. So the units of area would be what we call meters squared, because we're squaring length. So the unit would be a meter squared. That's called a derived unit, as opposed to a base unit. A base unit is one of these 7 in this list. A derived unit is something that you had to do something mathematically to it to get that unit. So there is no base unit of area. The area is a derived unit because we had to take the length unit and then square that. Okay, there are other ones as well. Volume, for example, is, for example, if you take a cylinder, and you fill it up with water, the volume of a cylinder is pi times the length squared, not times the length squared, times the radius squared, times the height. It's generally how it's written. So here's your height, and then there's your radius. So that would be a derived unit as well, right? What do you think the units of volume would be under these circumstances? Let me write it up here. Pi r squared h. Pi r squared is just the area of a circle. So the area of a circle in a cylinder times the height gives you the volume. Well, pi doesn't have any units, but radius is a length, right? So the units of that would be meters squared. And then height is a length as well, so that's another meter. So you get meters cubed. So no, we have a derived unit here. We took one of the 7 base units, in this case it was length, and we did something to it. So that gives us a derived unit. Okay. Now another aspect of measurements that's important is the idea of prefixes. These are used quite a bit. So we want to talk about prefixes here. Particularly when you do ALEKS problems, you'll see that prefixes show up quite a bit. Here are some common prefixes. Prefixes are powers of 10. It's just a way of using a letter to represent a power of 10. So we do this quite a bit. In the English system, we do it this way. You use these prefixes in a slightly different way. If I have the number 1,000, we call that 1,000, right? Now there's another term for that. It's called grand, right? So we might say it's 1G, 1 grand. In a sense, that's a prefix. The G is a prefix. It's telling us how many powers of 10. And we know that 1,000 is really 10 times 10 times 10. So how many powers of 10 is that? That's 3, oops, sorry here, 3 powers of 10. So that's one way. You know, then we have another one, right? We have this one. This is called a million, right? Capital M for million. Okay, there's your prefix. Again, a million is 10 times 10 times 10 times 10 times 10 times 10, right? Now what we're going to do is we're going to say, hey, instead of writing it out like that, let's just write it as 10 to the 6th. Right? 10 times 10 times 10 times 10 times 10 times 10 is 10 to the 6th. So here's a notation we can use, exponential notation, or scientific notation. And then here's a prefix. So we use those kinds of prefixes all the time in normal language, particularly now that money is not as valuable as it used to be. $1 million used to be an unreal amount of money. You know, now $1 million is a lot of money, but it's not an unreal amount of money. Now $1 billion is kind of an unreal amount of money. Okay, so I want to show you this table here. These are the prefixes you should memorize. You should memorize this table, quite frankly. Not the examples. You don't have to memorize the examples, but you should memorize the prefixes, the spelling of the prefixes, the symbols for the prefixes, and the meaning of the prefixes. And this is by no means a complete table. There are other prefixes that are used in the SI system, but these are the ones that we might use in Chem 1100 and in Chem 1200. I'm going to pronounce them for you just so you can see them. You know, I think of Terra chips when I see this first one. Terra is 10 to the 12th, right? So that 10 to the 12th, by the way, is a trillion, right? Giga, in the old days, some people would pronounce it giga, but I believe the proper pronunciation is giga, is a capital G, and that means 10 to the 9th, 1 times 10 to the 9th, which is giga. I'm sorry, I meant to say that it's a billion. 10 to the 9th is a billion. Mega, capital M, is 1 times 10 to the 6th, which would be a million, right? So mega. Kilo is a small k. I don't know why it's a small k and not an uppercase K, but it is a small k. And that is 1 times 10 to the 3. That's 1,000, right? Now we get ones that are less than 1. So these are fractions of 1. Deci, or deci. D, that's a lowercase d. So all the ones that are less than 1, the small ones are lowercase. So deci is 0.1, or 1 times 10 to the minus 1. Centi, small c, 1 times 10 to the minus 2. Milli, small m, 1 times 10 to the minus 3. Now we do have a way of talking about these numbers in the English system. A tenth, a hundredth, a thousandth, right? A millionth, a billionth, but again, we're going to use the SI system. So we're not going to use millions, billions, trillions, quadrillions. We're going to use kilo, mega, giga, tera. So, and deci, centa, milli. The next one is micro. This one uses a Greek symbol. Sometimes in the sciences, it's just history. Like before this system was completely thought out, people were coming up with different symbols and using them, and they just got integrated. So here's a Greek symbol. Micro, we know micro means small, right? Micro is mu. That's a Greek letter, mu. And that is 1 times 10 to the minus 6, or 1 over a million. Nano, nanotechnology, right? Small n, 1 times 10 to the minus 9. And then pico, small p, 1 times 10 to the minus 12. Okay, so there's your common ones. As I said, there are smaller ones and there are larger ones, but you're not going to see smaller or larger ones in your textbook. So this is how they're used. Look at the example column. A teragram is TG. So see how the structure of this? You put the symbol for the prefix next to the unit of measurement. So if I'm measuring grams, which is mass, a teragram is 1 times 10 to the 12th grams. So the tera is a number. So see what you're doing? You're using a letter to represent a number. That's kind of an interesting aspect of what we're doing, right? We're giving a letter to represent a number. Now, you've done that before. For example, pi, that's a number. That's a letter. Pi is a letter. ... E ... right? So those are letters that are being used to represent numbers. Okay. Now we take a look at some of the other ones. Kilo, 1,000 meters, a kilometer, a kilometer, a deciliter, a centimeter, a millimeter, a microliter, so forth and so on. So one of the things you'll find in this course and future courses is that we switch back between giving numbers and using prefixes all the time. It's a very common thing that we do. So for example, let me show you an example of this. If I say, look, the length is 3.5 times 10 to the 10th meters. That's a way of representing length, right? A number with a unit, right? And that's really what a measurement is. A measurement has a number and it has a unit. Okay? So what I might do is I might represent this number this way. 3.5 times 10 to the 10th meters is the same thing as 35 times 10 to the 9th meters. Do you know how I did that? Let me show you real quickly how I did that. What I did was I moved this decimal point over one space, so I got 35. So that's the same thing as multiplying by 10, right? If I take 3.5 and I multiply it by 10, I get 35. But you can't just multiply a number by 10 and say it's the same number. So what I did was I took the 10 to the 10th and I divided that by 10. And that gave me 10 to the 9th. So I multiplied by 10 for this one, but then I divided by 10 for this one. And of course, if you take a number, multiply by 10, and then divide by 10, that's okay. So 35 times 10 to the 9th meters. Now 10 to the 9th is giga. So I can also write this as 35 gigameters. Does that make sense? 10 to the 9th is giga. So 35 times 10 to the 9th is 35 gigameters. Okay? Let me show you another example of that. Suppose I have 1.45 times 10 to the minus 5 seconds. Can we use a prefix to represent this? Well, what I'm going to do is I'm going to look at the table, and I'm going to look for the prefix that's closest to 10 to the minus 5. And if you take a look, the one that's closest to 10 to the minus 5 is micro, right? 10 to the minus 6? That's only off by 1. So I'm going to make this 10 to the minus 6. Here's how I'll do it. If I move this 1 to the right, that would give me 14.5. But now I've got to divide this by 10, so that would be 10 to the minus 6 seconds, right? So what you do is you make this one bigger, and you make this one smaller. So if I make this one bigger by 1, I make this smaller by 1. Smaller than minus 5 is minus 6. So now you've got minus 6. So you can write this as 14.5 microseconds, right? Does that make sense? I like that one. Here, let's try another one. Let's try another small one. People often have more difficulties with the small ones than the big ones. So let's say we've got, let's find a length again. No, let's do mass. Let's do mass. Let's say our mass is 2.165 times 10 to the minus 10 grams. I don't want to use the kilogram for that one. Okay, so there's your mass. So now what we want to do is we want to find the prefix that's closest to it. So 10 to the minus 10, the one that's closest to that is 10 to the minus 9, nano. Right? Minus 9 is the closest to minus 10. So we need this one to get bigger by 1. So we need this to be bigger by 1. So I'm going to make it bigger by 1. So that means you got to make this one smaller by 1. Does that make sense? If you make one bigger, you got to make the other one smaller. So how do you make this smaller? I only needed to move it 1, so I'm going to move it 1. That makes it smaller. And you get 0.2165 times 10 to the minus 9 grams. So that would be 0.2165 nanograms. Does that make sense? Make one bigger, make the other one smaller. In general, if you're trying to get the prefix, what you do is you make the exponent, you change that one first, and then work on the decimal number. Now, suppose I'm going to take the same measurement, and I'm going to do the other prefix that is a possibility. So, even though nano is the closest one, pico's not that far off, right? Pico is only off 2, right? It's 10 to the minus 12. So let's do that. Let's make this 10 to the minus 12. Now, what did I do there? I made it smaller by 2, right? That means I need to make this one bigger by 2. Well, make it bigger by 2. 1, 2. 216.5 times 10 to the minus 12 grams. Does that make sense? These are both correct. So this one would be 216.5 picograms. So there's nothing wrong with either of those. They're both correct. And in fact, some people might want to report this answer in nanograms. Other people might want to do it in picograms. Perfectly fine. So make one bigger, generally make the exponent bigger or smaller, and then do the opposite to the number. Now remember, a measurement is a number. For example, someone is moving at 35, but there's also a unit. Miles per hour would be the unit of speed, right? So 35 miles per hour, a number with a unit. There's your measurement. Okay. Now, let's move on to some specific examples of calculations that we do with measurements. And the first one is temperature. And I'm not going to talk in great deal about temperature here. We talk more about it in the next course. The symbol for temperature is often a T, a capital T. And here's one of the issues with temperature. There are multiple units used with temperature. There is what's called the Fahrenheit, which is what we often use. The units of it is degrees F. We often use this with body temperature. We often use this with temperature of the environment around us on the earth. 100 degrees is hot. 20 degrees is cold, right? So we use those often. That's Fahrenheit. Another one which we'll use more often in this course and future is degrees Celsius. It used to be called centigrade. People don't usually use that name anymore. It's called Celsius now, but it used to be called centigrade. But one that you maybe have never even heard of, it's relatively rare to hear it even in movies and things like that, even like science fiction movies. Occasionally you'll see it in science fiction movies, is the Kelvin. And for us, this is actually a very important unit, and it's capital K. Notice it doesn't have a degree sign. There's one more that's commonly used, but only if you're an engineering major. You'll see this one's called the Rankine. So 3 of the 4 are what we might consider in this course. We're not going to talk about the Rankine system. But I do want to give you, for 3 of them, some baselines. And the baselines would be, the first one would be the freezing point of water. And the second one would be the boiling point of water. Fahrenheit, the freezing point of water is 32. Celsius is 0. Kelvin is 273.15. Boiling point of water is 212 in Fahrenheit, 100 in Celsius, and 373.15. Now the key significance here is that that's a difference of 100 degrees. I'm sorry, 100 Kelvin. This is also a difference of 100 degrees C. So the Kelvin and Celsius system are only different by 100. That's really the only difference there. So I'm going to write out a formula here that your textbook has. Kelvin equals degrees Celsius plus 273.15. There's your relationship. Sometimes that is just simplified down to 273. So here's a question. Suppose you're at 25 degrees C. There's your temperature. What is the temperature in Kelvin? All you got to do is add 273.15 to it. Sorry, this is 25. So if you want to know what the temperature in Kelvin is, you just take your 25 and add 273.15, and you get 298.15. And the units would be Kelvin. Now, I'm not going to get into the issue of significant figures because that's in the next section. Probably we would round this to 298 Kelvin, but that's not important for right now. The relationship between Celsius and Fahrenheit is a little bit more complicated. The temperature in Fahrenheit is 9/5 times the temperature in Celsius. Let's just write it as degrees C, sorry. Let me erase that. Plus 32. Okay? So here's what happens. Suppose the temperature is 0 degrees C. What is the temperature in Fahrenheit? You just take 9/5, multiply that by 0, and add 32. And that gives you 32 degrees Fahrenheit. The symbol for Fahrenheit is a degree F. Now, what also happens is, suppose you want to go the other way around. Let's go through it algebraically. Suppose you want to know what the Celsius temperature is. So I'll start here. By the way, 9 over 5 is the same as 1.8, so you can use that in this equation as well if it's easier for you. So if you want to know the temperatures in Celsius, here's what you do. You subtract 32 from both sides. Now, if you subtract 32 from the right side, you just get 9 over 5 degrees C, right? Because plus 32 minus 32 is 0. Now, what do you do with the 9/5? You got to divide by 9/5 from both sides. But if you divide by 9/5, that's the same thing as multiplying by 5/9. But notice there's two terms on the left. There's two terms there. So let's put a parenthesis in there. Now let's multiply by 5/9. Okay. Again, what I'm doing is I'm dividing by 9/5. Dividing by 9/5 is the same as multiplying by 5/9. So that's why it comes out like that. Okay. And that gives you degrees Celsius. So now let's just check real quick just to make sure that this is right. We have this table up here. The boiling point of water is 212 and 100 in Fahrenheit and Celsius, respectively. So suppose we do the boiling point of water. 5/9 times 212 minus 32 equals degrees C, right? We should get 100. So 212 minus 32 is 180. Five ninths times 180. Remember, 9 goes into 180 evenly. 9 goes to 18, 2. So that would be 5 times 20, right? So that'd be the same as 5 times 20. So that's 100. That's exactly what we wanted, right? 100 degrees C. Okay? So those are two temperature conversions that you want to work on. Fahrenheit to Celsius and vice versa, and then Kelvin and Celsius and vice versa. As I said, there's a lot in this section. They even put density in here. Okay? Density, let's talk about that real quickly because there's a lot of calculations we do with density. Density is the mass of a substance divided by its volume. I'm going to use the following symbols. D equals M divided by V. Okay? Now, let's go through a little bit of the algebra here. Suppose we want to know the mass. You just multiply both sides by V. So V times D equals, V over V is 1, M. Right? And suppose you want to know the volume. Well, let's take this intermediate step here. Let's divide both sides by D. D over D is 1. So volume is mass over density. So there's your three relationships. Density is mass over volume. Volume times density is mass, or volume is equal to mass over density. Now, remember, this is a derived unit. Density is a derived unit. Why is that? Well, it's mass over volume. So this is going to have a unit, and this is going to have a unit. Remember what we said? If you do an operation of combining units, if you square a unit, if you cube a unit, if you divide units, those are called derived units. There is no base unit for density. There's only those 7 base units. So this is a derived unit. So what would the units be? It depends on the units you're using. From the base, kilograms, that's the unit, the base unit for mass. For volume, volume is length times height times width. So that would be meters cubed. So in the SI system, this would be the units of density using the base units. But the problem is we don't normally use those in chemistry. In chemistry, we use grams, and then here we use cubic centimeters. Now, I'm going to write this as G over cm cubed, or G over cubic centimeters cc. This is the more appropriate way to write it, but you'll see this out there, particularly in the medical fields. Okay? So that's used in chemistry. So you're going to see different units used. That's just sort of the way it goes. Okay? So let's take a look at an example. The density of alcohol is 0.785 grams per centimeter cubed. What is the mass of 15 centimeters cubed of alcohol? Okay. All right, well, D equals M over V. We want to find the mass, so multiply both sides by V. So all we have to do is take the density and multiply it by the volume. So the density is 0.785 grams per centimeter cubed. And then the volume is 15 centimeters cubed. Now we're going to do something called dimensional analysis. Dimensional analysis is essentially based on the idea that we can do things with units kind of like what we do with numbers. What I mean by that is, suppose I had the fraction 1 over 7 times 7 over 3. Is there a way to simplify that equation, or not that equation, but that operation? See how you can take 7 and divide it by 7, and then just take multiply 1 over 3, right? 7 over 7 is 1, okay? So this is really the same thing as 1 over 1 times 1 over 3. So what you're doing is you're canceling numbers. You can do that with units too. So for example, if I have meters cubed over seconds, and I multiply that by kilograms over meters squared, I can simplify that by canceling 2 of the meters up here, meters squared, and making that a 1, and 2 of those. So that would just give me meters over seconds times kilograms over, sorry, I'm going to cancel both of those, 1, right? I canceled 2 of the meters, meters squared. So if you cancel the meter squared in the bottom, it's just 1. So this would be meters times kilograms over seconds. So you can do that with units. So notice what happens here. We have centimeters cubed here divided by centimeters cubed. So that just leaves us with grams. So 0.785 times 15 gives us 11.775. And then the only units left are grams. Again, I'm not going to worry about significant figures here. We would probably round this off to 12 grams, but that's fine. We'll talk about that in the next section. Okay, so that's using density. That's an important aspect. We'll look more at density a little bit later in the course, but that's an example of how to use it. Okay, so notice there's a lot in there. We're doing calculations. We're using units. We're doing dimensional analysis. It all is going to come into play here in this section.